Okay, so welcome to this next video in which we are discussing opioid receptors. Okay, so we're currently looking at the pathways downstream of the 4 opioid receptors. We've discussed that when the opioid receptor binds its ligand, what will happen is it will change conformation and it will then interact with a heterotrimeric G protein of the GI form, which means that the alpha subunit of that heterotrimeric G protein is either G alpha I1, G alpha I2, or G alpha I3. Okay, right. And we've discussed that the alpha subunit goes off to have effects on adenylyl cyclase enzymes. Okay, so for instance, all 3 of the G alpha I's subunits will go off and block the activation of adenylyl cyclase 1, 3 and 8, group 1 adenylyl cyclases by calcium, and also inhibit directly the adenylyl cyclase 5 and adenylyl cyclase 6 enzymes, which are group 3 adenylyl cyclases. And this will result in a reduction in cytoplasmic cyclic AMP, basically. Okay, right. So we now want to turn our attention to an actually more important downstream effect of the activation of the heterotrimeric G protein. And this comes about because of the beta-gamma subunit, not the alpha subunit, okay, which is rare in G protein signaling. Okay, so let's have the beta-gamma subunit here. Okay, and basically what's going to happen is it's going to go and activate a type of potassium channel that is within the family of inwardly rectifying potassium channels. Okay, so let me just draw the beta-gamma subunit for the time being. So here's the beta subunit in blue. Here is the gamma subunit in green. And then we've got the prenyl group of the gamma subunit, and that's shown here in orange. Okay, right. And what's going to happen is this beta-gamma subunit is going to go and bind to one of these potassium channels. Okay, and it's going to be an example of an inwardly rectifying potassium channel. Now I want to just briefly discuss what the structure of inwardly rectifying potassium channels is, because there are specific types of inwardly rectifying potassium channels that these beta-gamma subunits are going to go and interact with. Okay, so inwardly rectifying potassium channels. Okay, so basically they are tetramers, and I'm actually going to take this membrane a little bit further down here so I can draw the picture better. Okay, so they are potassium channels fundamentally. Okay, so they allow potassium to move through them, and they are made up of 4 separate proteins. So here is the inwardly rectifying potassium channel. It'll have a channel through the middle which will allow potassium to move through it, and then it's made up of 4 separate subunits. Okay, like so. So it's a tetramer. Okay, now let's take one of these proteins out. Okay, so 1/4 of the receptor. Let's take 1/4 of the receptor out in pink here, and let's have a look at its membrane spanning topology. Okay, so if we pull one of these out, then basically it will look like so. Okay, it has it has its amino terminus on the cytoplasmic side. It then has its first membrane-spanning alpha helix, then it loops back round. It tries to straddle the membrane again, fails, comes back, okay, and then completes another membrane-spanning alpha helix there, and then ends with its carboxylic acid tail here. So basically, this first membrane-spanning alpha helix is called M1. Okay, so this is called M1. Then the second membrane-spanning alpha helix over here is called M2, and then this portion in the middle is then called the P-loop. Okay, right, so we have 2 membrane-spanning alpha helices, a P-loop, and that's basically the structure of a single subunit of an inwardly rectifying potassium channel. Okay, you make 4 of these, stick them together, and you've then got your inwardly rectifying potassium channel. Okay, so The question is, how many different genes are there that code for these subunits of inwardly rectifying potassium channels? Well, the answer is there are quite a lot. Now, they are abbreviated to KIRs for potassium channel inwardly rectifying, basically. So, there are actually 15 different genes for inwardly rectifying potassium channel subunits. Okay, and these are grouped into 7 different families. Okay, so let's write this down here. So, the 7 different families are KIR1, then you have KIR2, then KIR3. Okay, and I'll bring this up a little bit. Then you have KIR4, KIR5, KIR6, and KIR7. Whoops, I've just missed out KIR5. Okay, so get rid of KIR6, put KIR5 there, and then put KIR7 here. Okay, so there are these 7 different families of inwardly rectifying potassium channel subunits. So the subunits of inwardly rectifying potassium channels are grouped into these 7 families. Okay, so basically there is only one member of this first family. So the only member of KIR1 is KIR 1.1 subunit. Okay? For the KIR2 family, there are then 4 members. Okay, there is KIR 2.1, KIR 2.2, KIR 2.3, and KIR 2.4. Okay, like so. Then you have KIR 3, you have KIR 3.1, you have KIR 3.2, you have KIR 3.3, and then finally KIR 3.4. Okay, so you have 4 genes in the KIR3 family. In the KIR4 family, you have 2 members, which again are sensibly named, and you'll agree, hopefully, that the naming for this is very sensibly done, and it's because it was done deliberately, basically. Okay, so all of these subunits also have their original names, and their original naming system makes no sense at all, okay? So it was renamed like this because it's a nice simple naming system, basically. But all of these have different names, basically, like Gurk and things like that, and that naming system is just very difficult to follow. Okay, because obviously they were all just named as they were discovered, and they were named different things because of the scenarios where they were discovered. Okay, now we can see that they all have this same sort of structure, and they're all being put together as inwardly rectifying potassium channels in tetramers, so we've organized their naming system, basically. Okay, so the KIR5 family only contains 1 member, that's the KIR 5.1. The KIR 6 family contains 2 members, KIR 6.1 and KIR 6.2. And then the KIR 7 family only contains 1 member, KIR 7.1. So let's now count all of these up and see that we have indeed got 15 separate genes. So here's KIR 1.1, then we've got 4 in the KIR 2 family, that takes us up to 5, another 4, 9, 11, 12, 13, 14, and then up to 15. So that takes us up to 15 different genes. Okay, right. So, basically, what you then have to do is you have to use these different subunits here to produce an inwardly rectifying potassium channel, okay? And this is where the complexity comes in, because you've got 4 different subunits in the actual channel, okay? So in principle, you could use any one of these 4 in each of these slots, and you could create an absolutely huge number of inwardly rectifying potassium channels. However, that is not generally found, okay? So, how do you pick which 4 subunits you're going to use in each of these 4 slots? Well, often what you find is that there are many different homotetramers, okay? And what this means is that the 4 subunits that make up the tetramer are all the same, okay? So you pick one of these 15 subunits that you want to use and you latch onto it, basically. You make that protein 4 times, you stick them all together, and that makes a homotetramer. Now, it's not always that simple. you can also make heterotetramers, okay? And this is basically where the 4 subunits that you've stuck together to make the tetramer are not all the same subunit. Now, generally, the rules go like this, okay? If you want to make a heterotetramer, firstly, you have to decide which family you're going to work with, okay? So you pick one of the 7 families. So, for instance, I might pick the 3rd family, KIR3, okay? You then say, okay, within the KIR3 family, I'm going to pick 2 different subunits, basically. So you might pick KIR 3.1 and let's say KIR 3.3. Okay, so let's pick those 2. And basically, you can now build a tetramer where you use those 2 subunits, okay? So that's how it works. You don't just mix and match whichever subunits you like. Firstly, you only use 2 different types of subunit, basically, in your entire tetramer, okay? In my case, I picked KR 3.1 and KR 3.3. And secondly, these 2 different subtypes have to be within the same family, okay? So generally, you don't mix and match. There are exceptions to that rule. Sometimes you will find heterotetramers where you've mixed and matched between the different families, but generally, the heterotetramers are formed from 2 different subunits which are within the same family. Okay, now, even then, not every heterotetramer that you could build from my rules that I've given you so far would actually be found in nature. Okay, but those are the general rules. And finally, you might ask, well, you've told me that we're going to make it out of these 2 subunits, but in what ratio, okay? I need 4 of these. Do I take 2 of this, 2 of this? When I've got those 2, how do I arrange them? Do I put both of the same ones next to each other? I.e., do I put 2 KIR 3.1s in these 2 and 2 KIR 3.3s in these 2? Or do I put them diagonally opposite each other? I.e., put the 2 KIR 3.1s here and here, and the 2 KIR 3.3s here and here. Those sort of questions, the answer isn't known, basically. What we know is that you can find inwardly rectifying potassium channels which contain KIR 3.1 subunits and KIR 3.3 subunits. We can't say in what ratios, or and we certainly can't say what's the actual positions of the different subunits relative to one another. Okay, so that's the basic rules that we know for assembling tetramers out of these 15 different types of subunit for the inwardly rectifying potassium channels. Okay, right. So, basically, when you build tetramers out of these 7 different families, the tetramers that are associated with certain families have certain names, basically. Okay, so let's start off with the KIR2 family. Okay, so if you build inwardly rectifying potassium channels out of the KIR2 family, okay, then those inwardly rectifying potassium channels, whether they're homotetramers or heterotetramers, will be called classical inwardly rectifying potassium channels. Okay, so these are called the classical KIR channels, or rather the channels which are built out of these KIR2 family of subunits are called the classical KIR channels. Okay, meanwhile, the inwardly rectifying potassium channels which are built out of this 3rd family here, these are the ones that we're going to be interested in. Okay, so it's the inwardly rectifying potassium channels that are built out of these inwardly rectifying potassium channel subunits in the 3rd family which we're going to be interested in. And these inwardly rectifying potassium channels are called G-protein gated potassium channels. Okay, so these are G-protein gated potassium channels. Okay, so they're assembled from subunits in this KIR3 family. Okay, and generally the 3 types of G protein gated potassium channels that you find. Obviously there are a huge number of types that you could build from the rules that I've given you. You could build the 4 homotetramers, and you could build many different heterotetramers. However, you don't generally find them. The main 3 G protein gated potassium channels that are actually found are KIR 3.1, KIR 3.2 heterotetramers, KIR 3.1 and KIR 3.3 heterotetramers, and KIR 3.1, KIR 3.4 heterotetramers, i.e. you mix KIR 3.1 with all of the other 3 basically, and those are the 3 main heterotetramers that you find within the family of G protein gated potassium channels. Okay, right. Then another really important family is this KIR6 family. This is incredibly important, but we're not going to discuss it in this video. Okay, basically the tetramers which are built out of members of this family are the ATP sensitive potassium channels, which are extremely important in the release of insulin in beta cells of the islets of Langerhans. Okay, and certain mutations in these channels have been associated with diabetes. Okay, so these are the ATP sensitive potassium channels. Okay, so why have I left out all the others? Well, all the others are then grouped into one final functional group, basically. So, if you build inwardly rectifying potassium channels from any one of the other 4 families, okay, so for instance, if you make a KIR 1.1 homotetramer, and that's the only one you can make out of this first family, or a KIR 5.1 homotetramer, these are within the family of potassium transport channels. Okay, so these are all considered potassium transport channels. Okay, so these are the families that are used to decide whether you can assemble heterotetramers or not, or at least to guide you in which heterotetramers can actually stand a chance of being actually existing. Okay, but these are the functional groups that actually tell you what these tetramers that you assemble from these subunits will actually be doing. Okay, so these are called the functional distinctions, whereas these are called the subunit distinctions. Right, okay, so why are we discussing all of this? Well, basically, beta-gamma subunits can bind to inwardly rectifying potassium channels of the KIR3 family. Okay, so of the G protein gated potassium channels. So beta-gamma subunits can bind to G protein gated potassium channels, which are potassium channels made out of subunits of the KIR3 family, basically. And the 3 main ones which exist are heterotetramers. They're all heterotetramers rather than homotetramers. And they're a KIR 3.1, KIR 3.2 heterotetramer. Then we've also got KIR 3.1 with KIR 3.3. That's another heterotetramer which is commonly seen. And then finally the other one is KIR 3.1 with the final remaining KIR subunit, which is KIR 3.4. So all of these heterotetramers are generally the G protein gated potassium channels that are seen. Okay, so what then now happens when the beta-gamma subunit comes and binds to our G protein gated potassium channel? Okay, so here's our G protein gated potassium channel. It's a tetramer. It's probably one of these tetramers here. Okay, so it has 4 of these inwardly rectifying potassium channel subunits, and it's sitting nicely in the cell membrane. And then along comes this beta-gamma subunit, and it's now bound to it. So what does this do? Well, it promotes the opening of these G protein gated potassium channels, basically. So what's now going to happen is this channel will open. Now, what happens when you open a potassium channel? Well, basically, potassium ions are going to move out of the cell. Okay, now potassium well, first I need to justify why potassium will move out of the cell. The reason is that potassium concentration in the cytoplasm is around 150 millimolar, and the concentration of potassium outside the cell is 4 millimolar. So you've got a nearly 40-fold concentration gradient favouring the movement of potassium ions out. Now, the astute ones among you will say, but hang on, you can't just say that. You're missing something. You need to take into account the electrical gradient as well. Okay, so let's take into account the electrical gradient. So basically, at the moment, the concentration gradient is saying move potassium out. So when we open a potassium channel, at the moment, we would expect potassium to go out according to the concentration gradient, but we do need to consider the electrical gradient across the cell. So, let's just make sure we're all on the same page with regards to what an electrical potential gradient is. So, basically, electrical potential is this concept from physics, okay? It is a mathematical model for us to understand reality. It's a mathematical structure that helps us to model the physical world, okay? And the idea is this, that to every point in three-dimensional space, you ascribe a real number, okay? So it can be negative, it can be 0, it can be positive, okay? It's just got to be a real number. It doesn't have to be an integer, it doesn't have to even be a fraction, it can be some crazy number like pi, okay? It's just got to be a real number. It can't be a complex number. You don't use a more advanced number system than the real numbers. You use the real number system. Okay, so you ascribe this symbol to every point in real three-dimensional space, and that number is called the electrical potential. So in principle, you can have a little man with a clever machine which can go to every single point and work out this electrical potential. Okay, and of course it does have some real meaning. Basically, it's how much energy you can get. Well, it's a measure of how much energy per charge that you can get out if you move it from that place away to infinity, basically. But don't worry about that. Okay? So, in principle, this little man can go around and measure electrical potential anywhere. Now, basically, all of the points outside the cell are in electrical equilibrium with one another and have the same electrical potential as one another. Okay, so all of the points outside the cell have the same electrical potential. So, this little man can go to a point outside the cell and he can measure the electrical potential of the extracellular compartment, and we'll call this big E for electrical potential, and then we'll subscript it E for extracellular. Now, this little man can then go into the cytoplasm of the cell and he can measure electrical potential there, and we'll call this big E subscript I for electrical potential intracellularly, okay? And the number here will not be the same as the number here. So basically, all of the points of the intracellular compartment are in electrical equilibrium with one another. They all have the same electrical potential, which is the electrical potential intracellularly, and all of the points extracellularly are in electrical potential with one another, at least in the near vicinity to the cell. So we'll call this the electrical potential extracellularly. Okay, now these two numbers will not be the same necessarily. Okay, so what we can then define is an electrical potential difference, or a voltage. Okay, and strictly speaking, we should say in what direction. So we should say the electrical potential difference from extracellular to intracellular. However, people often drop the from extracellular to intracellular and just say the voltage or the electrical potential difference across the cell membrane. Okay, but what they really mean is the electrical potential difference across the cell membrane if the little man moves from extracellular to intracellular. So what does this really mean? It means this little man is standing in the extracellular compartment and he has some number on his machine that measures electrical potential. Okay, so here is his machine and he's got this number on the screen. Now let's say he moves from the extracellular compartment to the intracellular compartment, and he gets a new number on the machine. The electrical potential difference from extracellular to intracellular, so he's moved from extracellular to intracellular, means how much does this number change when he moves from extracellular to intracellular. So what would I have to add to this number here to get this number here, basically? So this is going to be the new electrical potential, i.e. the number that he's got on his screen once he's moved, subtract the old number on his screen, so the electrical potential extracellularly, the number he had on his screen before he moved across the membrane. Okay, so usually the electrical potential difference across a cell membrane is around or somewhere around negative 65 millivolts. It does vary depending on what cell you're in. Okay, so smooth muscle cells, for instance, have an electrical potential difference of negative 60 millivolts across their membrane, whereas skeletal muscle cells, it can go as low as negative 95 millivolts, so it does vary. Okay, now what does this actually mean? Well, this means that if the little man moves from extracellular to intracellular, the number on his machine will go down, and it will go down by 65 millivolts. Okay, so the unit for electrical potential is the volt, so therefore the unit for electrical potential difference is also the volt, and millivolt just means 1,000th of a volt. Okay, so basically, if you move from extracellular to intracellular, the electrical potential goes down by 65 millivolts. Okay, that is what is meant by the electrical potential difference across the cell membrane. Now, potassium ions have a positive charge, okay, and that's what we're about to conduct through this channel. Okay, so positively charged ions like to be in places where the electrical potential is as low as possible. Now, which compartment currently has the lower electrical potential? The intracellular compartment or the extracellular compartment? Well, we know that the electrical potential difference across the membrane is usually around negative 65 millivolts, which means that the electrical potential of the intracellular compartment is lower than the electrical potential of the extracellular compartment by 65 millivolts. We don't know what the absolute values of these are, but we know that the intracellular compartment, whatever its electrical potential is the lower electrical potential of the two, basically. Okay, so the potassium ion is going to prefer to be in the intracellular compartment. So the electrical gradient is saying no. Move the potassium in rather than out. Move these potassium ions here in, because they want to be where the electrical potential is lower. So this always reminds me of Game of Thrones, because it's that scene, well, that episode in the first series where the old king has just died, okay, and the queen says that her son, Joffrey, should now rise to the throne, and the hand of the king says no, he should be put in charge, because the old king on his deathbed said that the hand of the king should rule until Joffrey came of age. Okay, and who wins, basically? Which one do the men follow? So basically, the concentration gradient says go out, the electrical gradient says go in. Okay, and basically the concentration gradient wins. It's the stronger one. It's Cersei. Okay, so she wins. She gets Joffrey in. Right, so basically potassium ions are going to start moving out, basically, because at an electrical potential difference across the membrane of just negative 65 millivolts, okay, the electrical driving force inwards is not strong enough to conquer the concentration driving force, which is favouring the movement of potassium out. In actual fact, you would have to take the electrical potential difference down to something around negative 85 millivolts, okay, where the electrical potential of the intracellular compartment is 85 millivolts lower than the electrical potential of the extracellular compartment. If you wanted the electrical gradient to equal this sort of a concentration gradient here, basically. So this electrical gradient is nowhere near strong enough, basically, to to neutralize the driving force of the concentration gradient. So at negative 65 millivolts, or in anything lower than negative 85 millivolts, you are going to get a net movement of potassium out of the cell whenever you open this extra potassium channel. Now, what effect does that have on the electrical potential difference across the membrane? Because you are moving potassium you're moving potassium ions out of the cell. Now, potassium ions carry a positive charge. So you are taking positive charge from the intracellular compartment and dumping it into the extracellular compartment. Now, when you remove positive charge from somewhere, that will reduce the electrical potential of that place. So the electrical potential of the intracellular compartment is going to go down. Then when you dump the positive charge into the extracellular compartment, the electrical potential there is going to go up. So positively charged ions make the electrical potential higher. So you're going to raise the electrical potential extracellularly, and you're going to reduce the electrical potential intracellularly. Okay? Now, we already said that when you moved from extracellular to intracellular, the electrical potential went down by 65 millivolts. Now we're making this one bigger and this one smaller, so the amount you're going to go down in going from here to here is going to get greater. Okay, so it's going to become more negative, and when the electrical potential difference across the membrane becomes more negative, that is called hyperpolarization. Okay, and this is actually a really important feature of the of all of the opioid receptors. Okay, they can hyperpolarize the electrical potential difference across the membrane of the cell that you're working with. Okay, and this is exceptionally important because generally these opioid receptors will be on presynaptic nerve terminals. Okay, so let's say this is the nerve terminal of some neuron. Okay, generally you will have these opioid receptors on these nerve terminals. Okay, and they will be then causing hyperpolarization of this nearby membrane, and what that is going to do is it's going to stop the release of neurotransmitter by this axon terminal and thereby reduce neuronal transmission across the synapse. Okay, but we'll discuss this more later. Okay, in the next video what we want to also see is how opioid receptors can also inhibit voltage-gated calcium channels.